So it's my honor to come here to give a presentation about some recent works on the derivation in our group. And also, I know that a lot of people are an expert on the large language models and the ASR, but I think derivation could also be very important to multi-speaker ASR. So I will talk about it. So the outline is basically, I will briefly talk about some earlier works about how do we get involved to the TSVAD pipeline of works. I know there are many other parallel systems like the END family of methods, but I think I want to take this opportunity to also introduce about the involvement about the TSVAD families of systems. Okay. And also at the end, I will a little bit talk about our system participating in this challenge using 2 or 3 slides to talk about derivation aware multi-speaker ASR using large language models. Okay, so I think this is a very standard definition about speaker derivation, the basic who spoke when problem. And then we start to participate, join this, study this question, actually be motivated by the Die Hard challenge, starting from Die Hard challenge 2. Before that, we haven't fully be aware of the difficultiness about derivation. And then you can tell from the name that Die Hard, because it's really hard to do well in the derivation. And if you look at the results of if you look at the data set up for the Die Hard 3 evaluation set, you can see that the number of speakers not much, the most is 10. However, in our daily lives, we encounter some problems where there are many speakers, maybe there are 15 or 20 speakers. So that the derivation test itself is very hard. If you look at the derivation 3 challenge at the challenge year, if you look at the performance at that time, I think the most difficult part was the meeting and online video and restaurant scenarios where the data is quite wild and a lot of many speakers. Okay, and then I'll briefly introduce about 3 different kind of pipeline families of methods. I think the first one is called a modular system. Actually, this is we call it conventional system. I think before we have like END or TSVD many systems, the people usually perform derivation follow different modules in a pipeline that people do the VAD first and then get rid of those non-speech segments, and then people extract speaker embedding for each of those short segments. Those short segments could be uniformly segmented, like 1 second segments. At the early days, people also do the speaker change detection. If you do a speaker change point detection, then you will get longer segment. But however, most studies right now or last time still use a short 1 second window. The reason is because speaker change detection, if you have one error, then you will end up with a speaker error of a very long segment that will give you very bad performance in the final evaluation metric, so that people try to segment it into small segments so that even though you make an error, it's just 1 second, it's not a 10 seconds or 20 seconds. Okay, and then once you get a speaker embedding, so you can calculate the speaker similarity matrix by doing the scoring, and then once you get a matrix, you can do clustering, you can get a result. Okay, and then also we have a END family. Basically, the most important thing at the END family is basically you use the PIT loss, because you have, for example, you have 2 speakers, speaker A and speaker B, and then the derivation result is relatively, it's not absolute speaker identity. So basically, there could be a flip between speaker A and the speaker B. So if you use the PIT losses, basically you will be able to calculate different permutations and then select the minimum loss. So in that case, that END works. And also later people have tried the END EDA or if you have a very long recording, you chop it into small segments, and then for each segment you perform the END, and then when you get the relatively robust estimation for small segments, now you do the global clustering on top of it to get your recording level result. This is how the END system works. And then also, people also try to work on the TSVD system. TSVD system at the beginning is two-stage problems, two-stage word models. And I will show you later that when you use online TSVD with sequence model, it's become a fully single-stage end-to-end models. But at the early days, people, when they start to work on TSVD, use the TSVD as kind of post-processing about clustering methods. I'll give you an example. So here, when you have the initial derivation result with either modular methods or END methods, then you get some segmented speech segments. And then what you can do that there are some errors, right? So you can extract speaker embedding and then do some like target speaker VED estimate. Basically, you want to estimate the timestamp for each target speaker. And then that actually quite useful to refine your initial estimations because it turns the clustering problem, is unsupervised, right? So unsupervised clustering problem into supervised VAD problem. Because supervised VAD problem basically means you have the first round of result, so you know there are three speakers, each speaker, how they looks like, right? And then you can register those three speakers, and then you can use the three speakers embeddings to test the whole audio recording so that it become a supervised activity detection problem. Of course, you can see that the performance will be quite improved. Okay, then I will quickly go over about some our in our group how our works got involved in this on this topic. So at the early days, I think 2019 actually is very nice talking with Hev. I think he's also the authors of the Pi anode. And then at that time, we believe that why people use a pointwise estimation about the similarity matrix. If you look at the similarity matrix on the right side, right, people at that time still use PLDA to estimate each point in the similarity matrix, and then you can see that it did not use the context information. So that if you use a LSTM or other models to row by row estimate the similarity matrix, you can better performance by better utilizing the context. Also, of course, later on the bottom on the right side, you could also directly estimate the similarity matrix by directly using the predict the sigmoid of Z and Z transpose. So and then at that time, so in this slides, we use many different results that extract from the earlier papers, so that you can also get an idea how the performance evolved. And also Die Hard 2 and 3 and other challenges, they have different setup by the colors, by the VAD, and so on. So that it may not be easier to compare with other methods, but you can get a relative trend. From here, you can see that compared to the PLDA, which is point-wise estimation about similarity matrix, if you use LSTM or tension to use some context, and you can get a better performance from 23 to 19 or 18. And then until 2021, and then I think that even they first proposed the idea of TSVD as a post-processing methods to refine the result from original clustering results. However, at that time, Evans methods still use I vectors at that time. And then in that paper, people tried a X vector, but that doesn't work well. So that we take some investigation about it. We think that if you want to do well in the TSVD-based methods in derivations, the key point is that the TSVD model's front end, especially the speaker feature extraction, is better to be the same as your speaker embedding extractor. So because if the front end, at the beginning, the feature extraction the same, then the system can well know about the relationship between the speaker, because speaker embedding at that time is just a linearly combination about the frame level features. When you have pooling layers, right? We have a pooling layers. Basically, you have a CNN or ResNet at the beginning, and then later on you have a pooling layers against speaker embedding. So if your TSVD's front end features also from the same front end, then basically it's better to model the relationships. Okay. And then people show that it's also our work. You can show that if it's on the CTS data of the of the Die Hard 3 challenge, and you can see that the first row is directly X vector and a spectral cluster and so on. And then if you add one round of target speaker VAD as a refinement, and then you can get a lot of improvement. If you get 2 rounds, you can almost get a half of that error reduction. Therefore, people think that TSVD could be a very good way to do the post-processing. However, it also this is another result. You can see that on the DieHard 3, these results are on the Oracle VAD setup, so that you can see that the numbers are relatively smaller. But you can also see that with TSVD as a post-processing and compare with and without, actually you can get clearly there are some benefits to doing that. Okay, and there are also other results on the I guess. Okay, there's our DieHard 2, DieHard 3, and the Vox Converse. There are also, you can see that with different pooling size, and you can see that the the results are different, but they all better than without TSVD. And then we get some criticism or get suggestions from reviewer said, okay, your TSVD message looks good, however, you still need a first round of clustering results in order to get the seed to get your target speakers. And at that time, we did quickly set up that we can also use the END methods to get to the first round, and then we get the END result, the target speaker that will directly prompt to the target. You can see the END result. We can get the target speaker embeddings, and then ES, and directly we can figure out trigger it integrated with our TSVD method. However, it's not elegant. It's a little bit. Just connecting two models together, and then you can open it to get the trainable parameters. And however, it's not very elegant. So that this is just a proof that we can actually also do the end-to-end methods all together. And then we also try the multi-channel TSVD. The idea is because sometimes we have multi-channel data, especially for the audio meeting or other meeting transcription scenario where you have a multi-channel microphone array. And then there are two different ways to do it. One way, I will show maybe later, that people try to use a directional arrival estimator, so that's a different location of different spatial information of different speakers, and use that to do the modeling. In our case, that we did not use that part. We basically here for the TSVD here, this is the top is speaker features, and then the bottom here is here basically when you get speaker features, you need to concatenate it with the target speaker embeddings. Here we have, because we have multiple channels of input speaker features, so that we use cross-channel self-attention, and right now in this industry we have another papers basically use both channel attention and cross-channel attention and cross-frame attention, and then basically you do this pooling, and you can see that the fusion, you can see that from the audio meeting evaluation data set. We actually, if you look at SC, this is SC means single channel TSVD from channel 1 to use here MCTS, which is basically the multi-channel TSVD. The multi-channel TSVD, the DR is approached to 2.26%. However, you use a single channel, you use 4.12%. So basically, by doing cross-channel attention, you can easily integrate multi-channel information into the TSVD family, the framework, and you can get nearly 40 or 50% error reduction. And we have also proved that in other databases as well, also on some real commercial applications that using the cross-channel attention to do the multi-channel TSVD actually helps a lot in real application, especially if you have a circular or linear array in your meeting transcription scenario. And then we also try to perform the online TSVD. So it's still a little bit not elegant. I just briefly show you how it works. It's basically you have the current feature XT, and you have previous left side feature XL. And then you do the front-end feature extraction, and then you get frame level speaker embeddings, and then basically you basically at that time you still concatenate it with your target speaker embeddings, and then you do some the backend, try to decode the probability of each speaker, and then once you get that, in the inference cases that you will have some rules to determine whether you want to add a new speaker or not. So it's not fully end-to-end. You still need to write some rules there to figure out whether you need to create a new speaker and so on. However, it's actually at that time it's actually performed very good performance on this, for example, audio meeting test sets, and this is 11.42. this is for the testing set, right? And then you can get this is online performance, and then if you use multiple channels, actually you will drop the performance to 5% if you use eight channels. This is for single channels. All right, and then I want to show you one important thing is when you use online TSVD, as I mentioned, that you want to use a little bit rules to determine the how do you aggregate the new speakers. We have experiment showing that when you want to update the speaker embeddings, right, based on the buffers, so do not use the overlapped part, because if you use because you already get the decoded voice activity result, and then you know that there could be a time frame that belongs to multiple speakers at that time, don't use that part to update your speaker embedding, because that will dramatically reduce the purity of your speaker embedding and the quality of the speaker embedding. Then will, because this kind of trouble will accumulate along the time, then eventually you are screwed up at the end of the decoding for the very long recording. So that's every time just use a single speaker segments when you of your decoded previous audios to update the speaker embedding. So this is for online TSVD, and it actually get very good performance. And then it's very easy to change the offline TSVD to the online just by if you take a recording and the first segment will become speaker 1, and then every time you do the target speaker embedding injection, if a new utterance speech and not belong to speaker 1, then maybe a new speaker you can add it to the buffer. So it's a little bit not elegant, but it actually worked well in reality, and then it motivates us to think about something better. Okay, and also this is at that time TSVD results. You can see that we get pretty good results. If you do online on the audio meeting, then you can get 4.5%. Okay, and then also we have online version of the models on the Die-Hard 3, even for the system VAD, then we can, at that time for online version, we can get 19%, which is quite good performance if you consider the online system. All right, and then this is still the modification from the what we call it more traditional TSVD pipeline. And then we also think about approaches by joint inference with ASR. The reason is we have figured out that the ASR, if you use conformer-based ASR, there are many layers, and then those layers actually, if you look at the speaker information, we have done experiments that if you use the first few layers of ASR conformer to do speaker verification, we figured that the first 4 or 6 layers give very good performance of a speaker verification, and then the upper level of layers is more related to semantic information. So that we try to see if we don't change, we let the ASR conformer to be frozen, and we only borrow the first few layers of the conformers and to do our speaker to the diarizations. Can we simultaneously achieve that we still have an ASR system doing well, and then we have little parameters to tune to get the sidecar model for the diarizations, and then you can see that here's the result. So if you use here's other competitive, this sequence TSVD I will show you later is our main, I think is a very good system. And you can see that if you directly use a simple like unified ASR and the speaker diarization models, where you can see error cases where you only have like 2.68 million parameters, and then you could still get similar performance as the sequence TSVD. Which means originally you need around 20 million parameters to train a diarization. So now if you still have an ASR to work with, and then so you can only tune that 2 million parameters, you can get same performance by borrowing some front-end features from the ASR. Okay. So starting until now time get involved to 2023, and then we try to think about what we can do to further improve the TSVD system, and this is important paper, because the later on our method all depend on this work, because I think this is the first time we try to decompose the TSVD works into a encoder and decoder separately. I will show you why we want to do that. Okay, just give you the first overview about the methods. You have acoustic features, and then those encoder part just serve as creating speaker related features. That's all. And then for the diarization, we ask the decoder to do the diarization. We don't want to merge them all together. It's just the encoder just serves as a feature extraction. And the decoder is trying to decode the activities. So here how that works. Here is existing target speaker embeddings. And here we get some augmented embedding. This is from other speakers, which is not in the recording. Okay, and then here the predict is when we predict a standard dimension vector, and this standard dimension vector with a linear layer, we can map it to real time t, which is a match with time domain input time. To be more specifically, previously, if you do the TSVD, so T is the time, and then N is how many target speakers, and then the F is your let's say MFCC features or F bank features, and the S is your speaker embedding dimensions. So previously we have to create a very big tensor and then do the TSVD method. Eventually you get a T multiplied N. N is how many target speakers, T is your duration. This is how original TSD model works. However, we try to decompose it to an encoder, which just serves as a feature extraction where you have F and T as input. And then here decoder, which is only try to map the input features to those N existing speakers. And then S by N is existing embedding matrix over there. So by doing this, we can decouple the T and N, because N could be very large and T could be very long. By doing that, we actually can significantly reduce the memory need, also the number of speakers we can work with. By using this setup, we can easily do more than 20 speakers in our setup with a very small, let's say, very small amount of parameters in the model. We can easily do 20 or 30 speakers. And then here example, we test our method, sequence-driven TSVD, on the voice converse dataset with a quarter 200 milliseconds. And you can see that previously we could not do well with 10 plus speakers, right? And then with this method, we can actually do quite good. Especially you can see that here we only got 10% DR on those segments with more than 10 speakers. So that this is a way to handle the multi-speaker, especially speakers more than 10, 20, 30, and then you use this sequence prediction to give you better performance. And then on the other hand, if you look at the performance on the voice converse test data, it also give you quite good performance, and we also get the challenge winner for that year. Okay, and then here we also get the result on under the HAR3 test set, and then you can see that with Oracle VAD, we can get like around 10%, and we'll show you that with system VAD we get around 15% about that. So this is the backbone of our subsequent two methods. May I know how many minutes I have? 5 minutes, okay. And then this is we recently published a paper called Online Sequence Neural Diarization. So we actually further improve the method by have two decoders. So previously we only have one decoder. So right now we have two decoders. The idea is that this is for the take input is the speaker embedding buffer, and the output is the predicted target speaker activity. This is as usual. Then we add a new one. New one is that we just feed it with voice activity timestamps we just learned from the previous decoder, and then we give this raw features from the whole recording, and then this representation decoder can automatically output speaker embedding. So basically, we create a model that can take the voice activity input together with the raw audio input, and then can directly give you speaker embedding. So by doing that, you can get like a twin system, like sister system. The first decoder give you embedding as input, the decode speaker voice activities. This The repetition decoder give you the voice activity timestamp. You can decode the speaker embeddings. So you can imagine that when you put them together, you can easily do online decoding. For the first, you can decode the segments, and those segments serves as the prediction of speaker embeddings, and speaker embeddings serve the prediction of next timestamps, and then going on. And you can do the chicken egg problem and then keep going. So you can see that this is how it works. I try to be brave so that you can look at how they can chicken egg going for the whole inferences, and then here you can see that. I'm sorry I can't be further, but its idea, a key idea is that based on the voice activity timestamp predictions, you can directly get the speaker embedding, and that's very helpful. Okay, and then this result are all based on system VAD on the diehard 2 and diehard 3. You can see that for online version, we can get 17%. And then for offline version, you can get 15%, which is also matched with the sorter. Okay, for system VAD result. And all our methods did not use any pre-training models like WaveRM or Wave2 vectors. So we believe that if you further use that one, you'll get even better performance. And also, this is our sequence-to-sequence neural diarization results for this is on the diehard 2, and then you can see that we get an online version. This is you can also get quite good performance, and this is diehard 3. Okay, so let me escape other, because we don't have time. We also do audiovisual diarizations. Maybe it's time limit. I can't go further to talk about it. I want to jump to this challenge. For this challenge, we actually propose a diarization-aware multi-speaker ASR method. And you can see that the idea is a little bit different from the BUT's excellent work. They basically plug in the diarization result to the whisper model to learn it. So we basically, our idea is that we feed our diarization result as a triplet. So here's the triplet. The triplet, first of all, you get a diarization result already, and then the embedding is your diarization system's output. The reason I think the most important thing is we want to say that embedding is useful. The reason is when you finish your diarization, you not only get a timestamp, you also get each target speaker's embedding. I think that each type of speaker embedding, if you're using the ARM, it will be useful. So how it can be useful? So we create a triplet where we have every target speaker, the embedding, and then the timestamp about the utterance. And then we put the embedding in linear adapter to the ARM. We put the timestamp linear adapter to the ARM. And here for the input meeting audio, we get a whisper encoder to encode the semantic information here, and we get a simple speaker embedding structure to extract the speaker embedding informations. And then for those two embedding matrix, we actually do a cross-channel attention to combine them, and then put adapter to the ARM. So basically here, if you look at the adapter, you have some speaker embedding information augmented here. And then here you have see the linear ARM. You also have the embedding information here. So that can create some kind of a relationship. We can teach system that these several frames are very highly correlated to this speaker. The reason that this speaker embedding is very similar to those speaker embedding features, right? And then why we want to have these precisely timestamp, because the system the challenge asks us to output the exactly timestamp. If you do not need to output the exactly timestamp, you can ignore that part. Basically, just each speaker give you the word. Okay, and then the model we use QN 2.5 is 3B, and then we train only on the English part of a common voice, and then voice splitting 2 and early meeting. So it's very small number of. We don't use many data, and then we can train it on the 8 NVIDIA GPU cards on a single machine, so that a university student can work on it with a single machine to train it. And then here is the instruction. Here is the instructions. Like our instruction quite simple. It's just showing you the triplet. Here's the target speaker embedding vector, and this is beginning frame of the input audio features. This is end of this triplet, this utterances, And your task is actually accurately transcribes the speech into those segments, and then the segment count must match with the timestamps and output exactly. So and then here you have this is your the multimodal input, and this is your result. So in order to let a system learn that you can only output the text that constrained by the timestamp, we actually perform some kind of augmentation, like a random replace, drops, shuffle, so that to make sure that if the triplet gives you something error, and other than the correct version, it will output nothing, and so on. So finally, we use quite a small amount of data with quite small amount of parameters of baseline, only Q1 2.53b. We can get around 18% about the final TCP WER. I think the winner is like 16 point something, I guess. But consider our model is so small, consider our training data so small, so that has some potential to keep improving to get better performance. Okay, so today I talk about spatial diarization, especially the TSVD family, about the involvement from the traditional TSVD to online TSVD to sequence-to-sequence TSVD, multimodal TSVD, and also to the diarization-aware multimodal multi-speaker ASR. So in the future works, I think currently in our lab, we are interested. One is the low weight, low latency online methods that could be used in the device side of the cell phone. On the other hand, we are also interested for the better utilizing the spatial information from microwave arrays to do the speaker diarization. This is mainly for the product of the meeting transcription like devices in the meeting room. And lastly, we are also interested in the multi-speaker ASR via ARM, because I think that ARM has a lot of potential. It has a very large models. So if you increase from 3B to 30B, 60B, you may get a very you can expect very good performance, right? So I think that integrating diarization result to the ARM may be a better potential, because ARM can have a very high bound, so that we try to use that direction. Thank you very much, and I want to thank the organizers and the students.